Okay, we're going to continue on here, and we've been talking about electrochemistry. And again, that is redox reactions, basically. So we talked about, again, oxidation, and that is when somebody will lose electrons and basically become more positive. We did reduction, which is when people will gain electrons and they become more negative. We look at, again, oxidation states as a way to determine what is going on. And if somebody's getting more positive, again, you can look at the oxidation state from the reactant side to the product side. And if you see it's kind of moving towards the positive direction here, that thing is going through oxidation. If their oxidation state is becoming more negative, is going through reduction. And remember that the thing that gets oxidized is our reducing agent, as it causes reduction to occur, and the thing that gets reduced is our oxidizing agent. And again, these things are found on the left-hand side of the arrow. We talked about balancing redox reactions in acidic and basic conditions. And again, in those situations, we add water to balance out the oxygens, and we also add H plus to balance out the hydrogens that are present. Remember, when it's all said and done, you need to be balanced in two ways. Again, like a normal equation, which means you have the same number of elements on each side, and the overall charge on each side of the arrow needs to be the same. Again, it doesn't have to be zero, but it does need to be the same. We then got into really what the chapter is truly about, which is galvanic cells. And galvanic cells in a laboratory basically have a kind of a setup like this. We have an anode compartment. We have a cathode compartment. Got some solutions. We have an electrode that is connected to each compartment here. We also have a salt bridge that kind of connects the two as well. And again, in the anode compartment, that's where oxidation occurs. So we're going to lose electrons. Electrons will travel through the wire here to the cathode side, which is sort of more positive. If you want to think about that, to kind of pull the electrons towards it. And that is where reduction occurs. Again, you're going to get guys jumping off the solid and into the solution. And over here, you're actually going to get guys to go from the solution out into the solid here as those electrons again come in to the solution. Remember, the salt bridge kind of purpose there is to make sure that you do not get the wrong buildup really of charge on the incorrect sides. Again, as we talked about, without the salt bridge, because this guy is going to be dropping ions into solution, it would create a much, much more positive side on the anode, and eventually it will stop the flow of electrons from going to the other side. Same thing over here with this positive guy leaving. You actually would build up a big negative charge over here on this side, which also would keep the electrons from wanting to go to that side. So the salt bridge, because it contains basically an ionic compound, will essentially send negative ions this way, and will send positive ions this way, in an effort to kind of keep the overall charge on each side of those sort of correct and what you need for that cell to continue. We can calculate the voltage of the cell, which is sometimes referred to as the EMF, or the cell voltage, or the cell potential, by using this equation that we talked about, I think, at the end, as the E of the cathode minus E of the anode. And remember that what we use is what is referred to as SRP values, and that's standard reduction potential. And it is a table, and it's a table full of reduction reactions. And because this is really a redox reaction that's occurring, one of these reactions technically does need to be reversed, and it should be the anode reaction that needs to be reversed. And because of that, there are a couple versions of this equation, or sometimes how people are taught. So the idea of that is when you reverse one of these, so we say the standard reduction potential for this guy is minus 1 volt. If we were to reverse that reaction, the top one, and make it an anode reaction, or oxidation reaction, we actually would change the sign of it. And you can do one of two things, as we talked about. If you want to change the sign on your anode reaction, you then should add both the cathode and the anode value together. If you do not want to worry about changing the sign that you find in the table, you should roll with this one, which is the minus version of it. And the minus version of it will change the sign of the anode for you. And again, that's why the subtract is in there. So again, as I mentioned last time, I'd probably pick one way and kind of stick with it. But technically speaking, though, if you were to write this half reaction and want to give the sort of E value for it, you should give it the appropriate one. And in this case, it would be positive because we reversed it. Or if you wrote sort of this half reaction, it would be negative. So it is sort of your preference. If all you need is cell voltage, you go to the table, find the two things, you can basically calculate. They figured out all those SRP values by using the standard hydrogen electrode or the She electrode and gave it a value of 0, basically hooked everybody else up to it as well. When you are not given any information about how the reaction is occurring, the one that is sort of the SRP values, you can use that to basically determine, which one's your anode and cathode, which we'll talk about here in just a second. Any questions on that stuff there? All right, so let's take a look. So here's a table. Again, as you can see in this table, they are all written as reduction reactions, which means, again, for your anode compartment, you technically would have to reverse one of those reactions of them as well. So let's take a look at this table, which obviously you could clearly not see, but they're all basically the same table. Let's talk a little bit about what we do when we do manipulate some of these guys. As I mentioned before, technically speaking, the E value that you see there is for the reaction as is written. So when you do go to one of these tables, it will again be all reduction reactions. Now, how do you know which one should be your cathode or which one should be your anode? If you are not given, as I was just mentioning a second ago, if you are not given any information about the reaction, how it's taking place, you're not given an overall reaction, you're not told in words how it's taking place, all you are basically told is you built this galvanic cell out of these two things. The one that is the more positive E value that you find in the table has a greater tendency to be reduced. And the thing that gets reduced in a galvanic cell is your cathode. So your cathode is usually the more positive E value. And again, if you're not given any information about how the reaction is taking place, that's how you know that's your cathode. The other guy would be your anode. Now, clearly, as I mentioned before, if you are given an overall equation or you're told how the reaction is taking place, then you do need to actually look and see who is being oxidized and who is being reduced, as that will tell you basically what it is. The half reactions are reversible, so definitely because they are all reduction reactions in here, you will need to, for your anode, basically reverse one of these reactions. And technically speaking, if you did reverse one of those reactions, as we talked about, the sign does change. So if we looked at our, again, our, do any of those there? We looked at our calcium, which is, looks like it's minus 287. Whoops, come here. So minus 2.87 volts for our calcium, gaining a couple electrons to make our solid calcium. Again, in this case, if we were to reverse it, the calcium would then go to this. This would be our oxidation reaction, and this would be our reduction reaction. And again, the E value here would go for our reduction. Our E value here would then be positive 2.87 volts in this case. So again, if you do flip it around, you would do that. That is what we were just talking about a second ago. If you choose to do that, which is perfectly fine, then again, you want to add those values together. You do not want to subtract them, otherwise you'll undo your change. But if you just want to take this one and know that's your anode, you can subtract it and it will change the sign for you. Now, changing the coefficients of the half reactions do not affect the E value that you find here in the SRP table. So what we mean by that is, as you know, you may have to multiply a half reaction by a common number. And in this case, you do not multiply the E value by that number. So different than like what you do in thermodynamics, where we kind of multiply, then we multiply the value there for, say, delta H. We don't do that. So if you needed to multiply a half reaction to balance out the electrons, you do not multiply the E value. It just stays the same. It's not affected by it. Any questions on that there? All right, so why don't you try one here? What is the standard EMF for this cell? Basically our cell voltage. Why don't you also write the balanced equation and ID the anode and the cathode, right? Okay, let's take a look. So again, in this situation, we're basically just told we're building two galvanic cells. They are under standard conditions, as we are 1 molar for each of those solutions. So in this case, we can use the SRP values. And by the way, this would come from our table or SRP table if you need to look it up. And we could use the one that is more positive will be our cathode, which means in this case, this guy is more positive, even though they're both negative. So this would be our cathode. This would be our anode, basically. So technically speaking, if we wanted the balanced equation here, our cathode one is fine the way it is. This guy technically would be reversed, which means we would technically have this, not that, goes there, plus that, and 3. And because we reversed it, technically speaking, this would be plus 0.74 volts the way that I wrote it. We also would need to add this equation and this equation together, but like normal, our electrons do need to be the same. So we would have to multiply the top guy by 3, bottom guy by 2. If I rewrite it underneath here, that gives us 3Cd2 plus 6 electrons goes to 3Cd solid. Again, by multiplying, it has no effect on the E value, so it stays the same. Here we'll multiply the bottom there, giving us 2CRS. It goes to 2Cr3 plus 6 electrons. Also multiplying does not affect the value here. So if we do this here, we add them together, our electrons, like a normal redox reaction, should completely cancel out, giving us 3Cd2 pluses plus 2CRS goes to 3CDS and 2CR3 plus in this case. Aqueous. This should be our balance. Again, if you look at it, we have 3 cadmiums on each side, 2 chromiums on each side. Overall charge here on the left is actually plus 6. Overall charge on the right is plus 6 as well. So it is balanced on both sides. Now, for the E of the cell, which is really what the question asks for, you could do one of two things. You could do your E of the cell is your E of your cathode minus your E of your anode. And in this particular case, what we would want to do is actually use our original values from the table. And that would give us our minus 0.4 volts minus a minus 0.74 volts. And that's going to get us there. A cell voltage 0.34 volts in this case. Now, alternatively, because I did switch the value here, my anode, I could actually just add these together because I switched the sign. And my E of the cell in this case would be minus 0.4 volts plus 0.74 volts, going to give me 0.34 volts. As you can see, you get the same deal, just that you switch the sign. Again, that again is what the subtract is for, to change the sign on this for you without you having to worry about doing it. So again, it's your call. But again, as I mentioned, don't change the sign and then subtract it. Otherwise, right, you're kind of undoing your change. Any questions on that there? Yeah. Why did I switch? I flipped the bottom one because in the SRP table, the R here stands for reduction. So every single reaction that you have in the table is written as a reduction reaction. And because the anode is actually oxidation, that means that the anode reaction in all these galvanic cells technically has to be reversed. Because the way it's written here, which was our anode, this is a reduction reaction the way it's written. So to make it into an oxidation reaction, you have to reverse it. And that's truly what's going on. And that really what that affects is really this value. Either you're going to have to change the sign, or again, you put it into the subtraction one here and it'll change the sign for you. No, no. And that's always the case because that table is, as we saw there, it's all reduction reactions. So the anode's always one has to replace. Other questions? All right, let's try this one here. Galvanic cell consists of magnesium and silver. Okay, so let's look at this. We're looking for the cell voltage. And again, we're under standard conditions. We'd go to the SRP table. Again, it doesn't really tell us how the reaction is taking place. So in this case, we can look at the SRP values that we find in the table. And we see this guy here is more positive. That means in this case, my cathode should be the silver. And this should be my anode. Once again, in this case, it really was just asking for the cell voltage. So if you want, you can just go right into this equation. I'm going to use here on the first one here is the subtraction, and that means I'm not going to change any sign I find in the table, as the formula here will change the sign for me with that negative or subtraction, and that is going to really change the sign here for our anode. And that's going to give us 3.17 volts in this case, which is good voltage. Again, if you're looking for the balanced equation, this would be the one that technically would need to be reversed. And that would get you magnesium going to magnesium with a +2 charge and our 2 electrons. And technically speaking, since we reversed it, our E value here would now become positive 2.37 volts. This is our cathode, which means it's good to go, but we do need to multiply it by 2 to get the same number of electrons. And that would get us 2 silvers plus 2 electrons gives us 2 solid silvers. And again, multiplying does not affect the value, so this would still be 0.80 volts. Here, this would give us our overall, where our electrons would cancel, giving us our balanced redox reaction here. That's basically occurring. And again, if you chose to do it this way to get E of the cell, because you did change the sign yourself, you could just add these together. And again, you'll get the same 3.17 volts. So again, your preference, whichever way you want to do it. Any questions on that one there? So when we talk about cell potential and electrical work, we can also talk about free energy. And remember, free energy is our delta G that we saw in our thermodynamics chapter. The work that can be accomplished by this sort of push of electrons is the difference there. 1 joule of work is produced or required when 1 coulomb energy is transferred between 2 points. The maximum amount of work that you could do is equal to Gibbs free energy in this particular case. And how that relates is we can have a relationship between Gibbs free energy and our E of our cell. And let's talk a little bit about a couple of these things here. Let's talk about each of these here. There you go. So first off, we do have this equation here, which is our delta G is equal to our minus NF E of the cell. The E of the cell here is what we've been talking about. This is our cathode minus our anode here. Our F is Faraday's constant, which is 96,500 joules per volt per mole. N is the number of electrons that is being transferred in this reaction. So as an example of that, what we just looked at there a second ago on that last one, I think it was. Maybe if I can find it, where to go. There it is. So when we look at these 2 half reactions here, N in this case would be 2. So you do not want to add these numbers together. It is the total number of electrons that's being lost by one and going to the other. So if you had something like this, N would equal 2 in this case, not 4. So that's really important. So it really is just the number of the balanced electrons in each half reaction, because those are the same electrons going from the anode to the cathode. And that is how you would get the N value in that particular case. And that would give us our delta G. And the relationship here is positive voltage is good. And that is because what we know with delta G is negative is spontaneous, right? And N is a positive number, F is a positive number, and that means that if your E of the cell is positive, along with the negative that's up in front here, negative and a positive will give you a negative value for delta G, which means the reaction is spontaneous. So when you get a positive cell voltage, that means you would expect a reaction to be spontaneous. Opposite is true if you get some negative cell voltage. That negative, along with the negative in front here, will turn our delta G into a positive, and this reaction would be non-spontaneous. So negative cell voltage is not good. It will give you a non-spontaneous reaction. Now, in addition to that, we can relate our cell voltage to our equilibrium constant, which is this one right here. And E of the cell is equal to RT/NF. In this case, R is the gas constant. It is the one that involves energy, the 8.314 version. So that is the R that we're doing here. Our temperature here, much like anything, needs to be in Kelvin. N is still our moles of electrons, and F is still our Faraday's constant. K here is the equilibrium constant, obviously, and E of the cell is still our cathode minus anode, right? So same deal in this particular case. Now, if you're at 25 degrees Celsius, basically the R, the T, and the F, they all become like a constant. And there's two versions of this equation that you sometimes see, and that is 0.0257 volts over N is the natural log of K, or 0.0592 volts over N is the log of K, in case you're a more base 10 log of K versus natural log. Now, do you have to worry about these two equations? The answer is no. You could just worry about this equation and just stick the numbers in. So you could just stick the numbers in for R, T, and F, and obviously it'll come out the same. So you don't really have to worry too much about those bottom two, but you will sometimes see people use those bottom two equations, especially when it's at 25 degrees. They kind of use the reduced down version of it. Now, this is our trifecta of goodness here, I suppose. We have E of the cell, K, and delta G. So obviously, we could go from delta G and E to the cell using this equation, E to our equilibrium constant, and obviously from G to K using one we saw in thermodynamics there between those two as well. Now, how does K relate to E of the cell and all that good stuff? It relates the same way. All three of these things, the delta G, the E of the cell, and the K value, they all three should agree with each other. So what I mean by that is if we have a positive value for E of the cell, we would expect the reaction to be spontaneous. And because it's spontaneous, that means we should be making more products the way it's written. And if we're making more products, we should have a large value of K. So all three of those things should, again, agree with each other. And opposite is true, obviously, if you had sort of the opposite situation, you had a negative value for E of the cell, that should lead you to a positive value for delta G, which means you mainly should have reactants at equilibrium. And if you mainly have reactants at equilibrium, you should end up with a small value of K. So again, if you're doing problems, you have to calculate multiple of those things in that problem. That's a good way to check yourself. They really should sort of all agree with each other. So for example, if you got a positive voltage and a super small K, probably something went wrong with your calculation. And my guess is that a lot of times what goes wrong with calculations are like negative signs. People forget to put the negative or put a negative when there shouldn't be. So you just got to be really careful with the negatives as you're going through it. Speaking of negatives, this one here does not have a negative, which is also a very common error. People want to always kind of put a negative in front of the RT over NF in this particular equation. Any questions on that there? All right, so that is sort of what we were just talking about. Again, those things should agree. Negative G, large value of K. We should have a positive value of E. And again, positive value of delta G should give you a negative E of the cell and a small value K. If you're at 0, you're going to have an equilibrium constant of 1, and because everything else will basically cancel out. All right, so why don't you give it a go here. Calculate the delta G not for this reaction, and is this spontaneous? And then again, these are some of your SRP values here on the table. Okay, so let's take a look. So in this case, we are given an equation, so we should take a look and see what's going on. That's +2, that's 0, that's 0, and that is +2 there. So our copper, right, is going from here +2 to 0, becoming more negative. So that is going through reduction, and that means that is my cathode. Here, the iron is starting at 0 and ending at +2. It is becoming more positive, which means it's going through oxidation, and that is my anode in this case. So we can use our delta G is equal to minus NFE of the cell. Our N in this case is the moles, and in this case it is 2 electrons, right, that is being transferred. Our F is a constant, our Faraday's constant, 96,500 there, joules per volt per mole. And our E of our cell, in this case, I'm not going to change the sign, so I'm going to subtract. So it'll do it for me. Now that I've identified my cathode as the copper, we're going to take 0.34 volts minus a minus 0.44 volts. That's going to take care of my anode change right there. And that is going to get us here, looks like 0.78 volts in this case. So now we have everything we need to calculate delta G. So our delta G will equal minus our N, which is our 2 moles. Our Faraday's constant, 96,500 joules per volt per mole. And our E of our cell, which is 0.78 volts. Volts are going to cancel, moles are going to cancel, going to leave us joules as our answer here. And looks like something negative 150,540 joules are roughly minus 151 kilojoules, which is sometimes what delta G is usually given in, which is kilojoules. In this case, this reaction is spontaneous. Yeah, we knew that actually when we hit the positive E here with a positive E should lead us to a negative delta G. And by the way, if we calculated K, we should probably have a large value of K in this case, right? Over 1, as that all would make sense. Any questions on the calculation there? All right, so why don't you try this one? Will 1 molar nitric acid dissolve gold metal to form 1 molar gold 3 ions? Again, your SRP values there are on the bottom. Okay, let's take a look. So in this case, our cathode is which one? Our cathode is this one. It's our cathode. This is our anode. So why is that? Even though this one's more positive, it is because of what it says in the question. It wants to know, will nitric acid dissolve gold metal, which is gold with no charge, to form gold with a +3 charge. That would tell me +3 has got to be on that side. I got to reverse that guy, which means that's going to be my anode in this particular case. So again, it's really important to make sure you follow what it says in the question, or if they give you an equation, you actually look at it. Again, you only go with the more positive one if there is no information about how it's reacting, other than it just says you put these two together. So because of that, this is actually going to be my anode. So my E of my cell in this case would be my E of my cathode minus the E of my anode. And in this case, my cathode being really the nitric acid, which is right there. And that is 0.96 volts minus my gold, which is actually my anode in this case. And that's going to get me there a minus 0.96, subtract 1.5, a negative 0.54 volts. And really at that point, I actually know this reaction is not going to happen. And that is because this is a negative voltage, which I know from our conversation a second ago, that if I took that negative voltage here with a negative there, that's going to give me a non-spontaneous positive delta G if I were to calculate the actual value in this case. So this reaction would not happen. It's non-spontaneous. And that is how they check sometimes, right? To make sure your gold is real, they put nitric acid on it. And if it's still there, it's good. If it's not, then not so real to your gold, because it should not react with it. Yeah. Any questions on it? Yeah. Not the way I did it, because I subtracted. So when I use this equation, the subtraction version, you don't flip the sign, because that's what the subtraction does for you. Now, if you did flip this guy, you would change the sign. It'd be minus 1.5 volts. If you flip this guy around to AU goes to AU3 plus the 3 electrons. Because you flipped it here, you then should, if you want to calculate the E of the cell, is actually add those numbers together with the sign already flipped. Yeah. Yeah. So you don't want to do both. So if you flip the sign, which is perfectly fine, you just actually need to add the numbers at that point. If you don't want to worry about flipping the sign yourself, that again is what the subtract is for in this version of the equation. And it's because it's always minus the anode, which is always the one that needs to be flipped. Other questions on it? All right, so let's take a look here. What is the equilibrium constant for the following reaction? Bless you. And here's your SRP values there. See what you come up with. Look for the K here. Okay, let's take a look. So we're looking for equilibrium constants. So I'm going to go with the equilibrium constant equation we saw, RTNF, natural log of K. We do need our E of our cell here. R obviously is a constant. T is 25 degrees, needs to be converted into Kelvin, so add 273. Here we want to look and see what's going on. So our iron is going from +2 to 0. Our silver is going from 0 to +1. That means actually in this case, our silver is our anode as it is being oxidized. And our cathode actually would be our iron. So once again, because they did give us the equation, we need to look at it and see what is going on. And again, our iron is, if you're following on the sort of number line deal, going from +2 to 0, so becoming more negative, and the silver going from 0 to +1, becoming more positive. So with that being said, again, I'm going to not switch the signs, so I'm going to subtract. If you switch the signs, you should add, obviously. So here we'll go with our cathode, which is minus 0.44 volts, minus our 0.8 volts in this case. That's going to get us a negative 1.24 volt. Really, right off of this calculation, I know this reaction is spontaneous or non-spontaneous. This reaction is non-spontaneous because it is a negative E, and that means that should give me a positive G, which means it's non-spontaneous. That also means when I calculate my equilibrium constant, it should be a small value, right? So again, that's the things you want to think about. So if we pop our numbers in here, negative 1.24 volts equals our R, 8.314 joule per Kelvin per mole, our 298 temperature, divided by N. N in this case is 2. Yeah, I know that because that is a +2 that goes to 0. So that is a +2 change. And the silver will be a +1 change, but there's 2 of them, which also means it's 2 electrons total being lost in this case. So N is 2. And our Faraday's constant is a constant, 96,500 joules per volt per mole equals our natural log of K. So I'm going to clean up here on the left-hand or right-hand side, with the left-hand side of the right-hand side, I guess. So 8.314 times 298 divided by 2 and divided by 96,500. Going to give me something like 0.012837 natural log of K equals minus 1.24 volts. I obviously can divide that to the other side now. And I'm going to take the whole number on my calculator. And that's going to give me a minus 96.595 equals the natural log of K. I need to then E both sides. That's going to get rid of the natural log on this side, leave us with K. Although I rounded it on the paper there, I am going to take the whole number in my calculator, not the rounded number. And I'll get 1.1 times 10 to the minus 42, which I would say is a small value of K that goes with our negative value for RE. Now, I will say, depending on your rounding around here, you may get a slightly different front number. But the back number here, or the exponent number, should be the same. So depending on the rounding, you might get a slightly different number when you kind of do the E version of it. I personally just don't round on my calculator. I just take the whole number that I have and kind of do it from that. Question on any of those there? And again, as I mentioned before, you should have agreement between these two things for sure. And also the delta G should also agree with it as well. Any questions on that one there? Okay. So let's talk a little bit about the effect of concentration on this cell EMF. And we have standard conditions, as we've been talking about. And again, a reminder, when you see in any of these things, the E, the delta G, right? You see the little knot symbol. That usually means standard conditions. And a reminder that basically standard conditions is if you're dealing with something with concentration, everybody needs to be 1 molar. If you're dealing something with pressure, 1 atmosphere is basically the standard sort of conditions. It's kind of the table conditions that you find things in, although really not part of standard conditions, but sometimes people consider it that way. Is 25 degrees Celsius is a normal sort of temperature, but these are the main 2 that you want to see. Now, as we saw, we had a delta G in the thermodynamic chapter where we had non-standard conditions. And we also have obviously delta G here. Putting those together gives us an equation which is known as the Nernst equation to figure out the cell voltage under non-standard conditions. And basically it's almost identical-ish to that one in terms of what we're looking at. This is basically our E of our cell under non-standard conditions is a way to think of it. This is our normal E of our cell under standard conditions. And that would be you go to the table and do your cathode minus your anode. RT, NF is all the same that we were using previously. And the natural log of Q. And remember, Q is the reaction quotient, and Q is calculated basically the same as K, right? So Q is the concentration of products divided by the concentration of reactants, just like we do K. We also could do it with pressures as well. So if you had something that involved pressures, right, you could do it with the partial pressures of your products divided by the partial pressure of reactants as well. Now, just like we saw with that previous equation, if you're at 25 degrees Celsius, the RT and F does reduce down to those same numbers we saw previously. Once again, if you don't want to worry about the bottom 2, just put the numbers into this equation and it'll work out just fine. By the way, if you cannot remember the previous equation, it had the equilibrium constant, but you can remember the Nernst equation. That is where that equation comes from, is actually the Nernst equation, because at equilibrium, E is equal to 0, and Q would equal K, which would give you this equation, 0 equals E naught minus RT NF natural log of K. You would take this entire thing and add it to the other side, and that would give you that equation that we saw previously, RT NF natural log of K. So that is basically kind of where that equation comes from, and also why there is no negative, and that's why people put negatives in that other one, because they see the negative here and they think about it. So again, just keep that in mind. So you would definitely want to use this if we're not under standard conditions. And like I said, the two major sort of reasons that would be molarity is not 1 molar, are for everybody, the pressures aren't 1 atmosphere. So let's take a look at one here. For the following, will the following reaction occur spontaneously at 25 degrees? And again, there's our SRP value. So give it a go, see what you come up with here. Look, so first off, I see some concentrations here, and they are not 1 molar. So that makes me think non-standard conditions here. Because it's non-standard conditions, then that's probably our Nernst equation we want to use. So cell equals or E cell naught minus RT NF natural log of Q. In this particular case, we do want to figure out what's going on. They did give us an equation. So this is +2, 0, 0, and +2. Again, in this case, our iron is going from +2 to 0. It's actually being reduced in this case. That means our iron, even though it has a maybe more negative there, is going to be our cathode. Our cadmium is going from 0 to +2, losing electrons, being oxidized, which would be our anode. So we can't calculate E of the cell under standard conditions. And once again, I'm going to subtract because I'm not going to change the sign. And as usual, if you did change the sign, you should add them together. And you would be changing the sign of the anode in this case, by the way. And that would give us minus 0.44 volts, minus a minus 0.4 volts in this case. And that's not giving us much here left, but we will end up with looks like negative 0.04 volts. So under standard conditions, this reaction is not spontaneous, right? Because we do have a negative value here for our voltage. We also need to figure out our Q. Our Q in this case would be our products over our reactants. And we are only taking things that are aqueous, so cadmium, in this case, divided by the iron. And that is why we only have 2 concentrations, because these guys are solids and not included. So we don't have to worry about those. So if we put those guys in there, our cadmium is 0.01 divided by 0.6 in this case. And obviously, if there was some coefficients, you would need to do some squaring or whatever it may be, but there is none in this case. So a bunch of 6s here. And I think for the most part, our temperature here is going to be 298 Kelvin as we add 273 there. And our N in this case is going to be 2. Once again, I know that just based on +2 to 0, that's a difference of 2 electrons. Also 0 to +2, also a difference of 2 electrons. So 2 is the number of electrons that are happening in this case. Again, basically because our iron is taking 2 electrons there to go that way, and that would be 2. And our anode reaction actually would be something like this. And over there, right? So that is basically where our N comes from. I think that is everything we need. F is a constant, so our E here of our cell going to be our negative 0.04 volts minus our R. 8.314 joules per Kelvin per mole. Our T, 298 Kelvin, divided by our N, which is 2 moles, and our 96,500 constant for Faraday. And that's going to be our natural log of 0.01667. I'm going to clean up everything over here, I think. So I still have the unrounded number in my calculator of Q. So I'm going to take the natural log of it using the whole number in my case times 8.314 times 298 divided by 2 and divided by 96,500. That is going to get me here still negative 0.04 volts minus now a minus 0.05256 volts basically. So finishing out here, minus 0.04 minus my answer there, going to yield me a whopping voltage here of 0.013 volts in this case, yeah. This is going to be a positive voltage, not a lot, but it is enough to make it somewhat spontaneous, yes, in this case. So here, by changing the concentrations, we're able to make a reaction under standard conditions that is non-spontaneous into one that is, well, slightly spontaneous here, as it's got a little bit of voltage.